Yeah, so hello, welcome to the fourth session of the second season of the Isogeny Club, I believe we're at. Before we start today, I just wanted to mention that the Eurocrypt 2023 registration is now open. And be sure to also register for the affiliated event. So that you can take part of the Isogeny Club workshop, which brainstorm session, which will happen on the Saturday. Also, in relation to that, if you have any good ideas that you would like to present there so that we can discuss them together and work on them, then that would be great too. Yeah, you can look at the website to find more information about how to submit these. Okay, without further ado, today that's not why we're here today. We're here to listen to Michael Meyer give a talk on fantastic peas and where to find them. So Michael is a postdoc at the University of Regensburg, and during Corona, I believe he had an internship as a pirate, but he's now focusing full-time on isogeny-based crypto. So yeah, take it away, Michael.
Thanks for the very accurate introduction, Jonathan. And thanks for having me here at the Isogeny Club. So this talk is about two papers I was involved in. So one was joint work with Craig Costello and Michael Meyer from Eurocrypt 21, I believe. And the other one is more recent work, joint work with Giacomo Bruno, Maria Gabriel Santos, Craig Costello, Jonathan, Komada, Eriksen, Michael Meyer, and Bruno Sterne. Most of these people actually have given talks here in the Isogeny Club already, so probably you know most of them already. Yeah, and this talk will be about SQISign primes, although that's not that accurate actually, because I'm not going to talk much about SQISign and I'm not going to talk much about primes. But I will talk about a related problem that is finding so-called twin smooth integers. But that's very much related to finding nice primes for SQISign. So yeah, I just want to give a bit of an overview about these twin smooth integers and how that relates to SQISign. But first of all, today is a very special day, 14th of March. So happy Pi Day to all of you. And actually, having this talk slot here came with some very special requirements. That is, Krein sent me this message here. So I'm very sorry in advance for any really bad Pi jokes that might occur during this talk. And also, I'm not really sure why Jonathan Krein chose me for this very special talk here and for including many Pi jokes. Well, best guess is because I'm an isogeny pirate. Krein's laughing, that's a good sign. Yeah, sorry for that. For those of you who don't know that, that's a conference video that we made for PKC 2020, and Jonathan referred to that in the intro. So that's actually a pirate video, and you can find that on YouTube, on the IACR channel for PKC 2020. Okay, but let's get to the actual content of this talk. So as I mentioned, most of the talk will be about twin smooth integers. And so the first part will be some sort of motivation, why this is interesting and why this relates to isogenies at all. And then I'm going to talk about how we can search for such twin smooth primes, twin smooth integers that then can generate parameters for isogeny crypto. The third part is about different methods of finding twin smooths, which will be more constructive. And then the fourth part will actually talk about the SQISign requirements and some concrete parameters for SQISign. Okay, but first let's start with a small example of why this is interesting at all. So just to start with SIDH, although that's broken, as everybody knows probably. Yeah, but it's a very good example to see what's going on here and what's the problem we're interested in. So if we look at a toy example for SIDH with this nice prime, 431, which is 2 to the 4 times 3 to the 3 minus 1, then we work with curves over fp square such that the cardinality of the set of points is p plus 1 squared. And by the construction we use in SIDH, Alice then computes the secret 2 to the 4 isogeny, and Bob computes the secret 3 to the 3 isogeny. So they're computing some paths through these graphs. By the way, I stole these graphs from Craig Costello, so thanks, Craig, for putting the slides online. Yeah, so the main point here is that we have points of order 2 to the 4 on the curve. So we can carry out all these computations on Alice's side, the secret 2 to the 4 isogeny, only with points over fp square. So we don't have to move to extension fields, and everything will be very efficient. And the same is true for Bob. Bob's computing the 3 to the 3 isogeny. We're having points, all the points of order 3 to the 3 on the curve, so everything will be very efficient here as well. But one thing we can notice here already is that the number of different curves or different J invariants in these isogeny graphs we can reach by these secret isogenies is roughly square root of p if the power of 2 and power of 3 are balanced out somehow. While the full graph has p divided by 12, roughly p divided by 12 J invariants here. So we're actually only reaching a very tiny fraction of this isogeny graph here with these secret isogenies. And so this seems like, yeah, there's lots of structure that we don't actually use. And it seems like we're using parameters that are actually way too large for the security we want to have. And that's the main idea behind B-side by Craig Costello. And first of all, B-side is broken as well. Maybe I should mention that this year too. So the main idea here now is that Alice works with the same curves that we saw before. So the curves over fp square with cardinality p plus 1 squared. But then again, these curves have quadratic twists with group order p minus 1 squared. And this means that those curves will be isomorphic over fp to the 4, but not over fp squared. But anyway, all those isomorphic curves, even if they're isomorphic over fp to the 4, they have the same J invariance. So Alice and Bob basically, while using curves with different group orders, they move in the same isogeny graphs. So these are the J invariants here, and as you see, those are exactly the same on the left and the right side. And what we can do now is we can now let Alice compute the secret isogeny of degree p plus 1, because we have all the p plus 1 torsion defined over fp square on Alice's curves. So Alice can compute 2 to the 4 times 3 to the 3 isogeny. And on the other hand, Bob can use almost the whole p minus 1 torsion for his isogeny. They have to be co-prime, so he can't use the factor 2 here. But Bob can use all the other factors of p minus 1, which would be 5 and 43 in this case. Of course, the isogeny degree here is a bit larger with 43, so things will be less efficient on Bob's side. But anyway, with the same size of prime that we had before, we can now reach basically the full graph and not only the small fraction as before. So basically, it all boils down to what we call accessible torsion. So on Alice's side, all the p plus 1 torsion is defined over fp square, and on Bob's side, all the p minus 1 torsion is defined over fp square. So we can compute isogeny for all the prime divisors of p plus 1 or p minus 1 very efficiently. And although B-side is not that interesting anymore since it's broken, we're using the same in SQISign. So maybe you've seen the SQISign talks by Jonathan or by Antonin. And basically one of the tasks we have to perform in SQISign is we have to compute isogenies of degree roughly p to the 5/4. So only using this SIDH smooth part here for p+1, we wouldn't have enough accessible torsion to compute all these isogenies over fp squared and to have them, to compute them very efficiently. So what we're doing in SQISign, we're using small prime factors of both sides, p+1 and p-1. And the good thing here is that, even though those curves are isomorphic over fp4 and like having a point of the full order p+1 times p-1, we need to move to fp to the 4. We can actually compute the individual isogenies over fp squared. So yeah, everything is very efficient here. And yeah, for more details on that, you can check out the B-side paper by Craig, where he explains how to compute everything here in over fp squared. All right, so what we've seen is we want to have small prime factors of p-1 and p+1 here in this case, right? So the problem is we need to find primes p of a fixed size. So for example, for B-side and SQISign, this would be 256-bit for NIST-1, 384-bit for NIST-3, and 512 bits for NIST-5, such that both p+1 and p-1 are as smooth as possible. And what do we mean by smooth? B-smoothness means that for some bound b is larger than 0, an integer is B-smooth if all prime divisors q that divide this number m are smaller or equal b. Right, so we want all prime divisors of our number to be smaller than this bound b. And related to that, we define so-called twin smooth integers. And by that, we mean pairs of B-smooth integers, m and m+1, such that both m and m+1 are B-smooth for some b larger 0. And now with these twin smooth integers, we can rephrase the problem above. So instead of saying we want to find a prime such that its neighbors are smooth, we can now say, okay, we want to find B-smooth integers, m and m+1, of a given size, with b as small as possible, as above, such that their sum to m+1 is prime. So this means we define p as 2m+1 and it's prime as above. And the neighbors of p, p-1 and p+1, are actually 2m and 2 times m+1. And by construction, because we use those twin smooth integers here, they will also be B-smooth. Okay, so now the question is, why do we rephrase the problem like this? So finding primes is not that hard, right? So taking some random numbers of those 256-bit or something, we will, we can simply use the prime number theorem, and with something like probability 1 over log p, we will find a prime if we choose some random number of this size. I mean, the prime number theorem, of course, is only gives asymptotics, but in practice for these sizes, it gives a pretty good bound for probabilities here. So finding primes is basically as easy as pi. But on the other hand, finding smooth integers here of these sizes will turn out to be very hard. Okay, before we get into these probabilities, let's look at some examples. On the left side, we have the 5 smooth twins. So all the pairs m and m+1, such that both are 5 smooth. So we have prime divisors at most 5. And this is actually the complete list here. So 80 and 81 is the largest pair here. So we can't hope to find B-side or SQISign primes that have 5 smooth neighbors. And on the right side, there's the 19 smooth twins. And the 2 green ones there are actually the largest ones as well here for 19 smooth twins. And for really small smoothness bounds, there's actually a method to compute all of them pretty efficiently, as we will see later. All right, so let's get to the first part here, searching for twin smooths. Okay, for this, we first look at some smoothness probabilities. So we define this function psi of n and b. And with this function, we count all the integers m that are between 1 and this capital N, where m is b smooth. So this simply counts all the b smooth numbers up to this capital N. And then we can compute the smoothness probability for a random number up to n, which then is this function psi of n and b divided by n. And we can compute this actually by the Dickmann-de Bruijn function, which is written as this Leroux function. Yeah, we compute this as a rho of log n divided by log b. This again only holds asymptotically. But for the sizes we're interested in, this actually gives a pretty good bound. It's pretty accurate. So as an example, if we pick a random number up to 2 to the 256, and we want this number to be 2 to the 16 smooth, then we can compute this psi divided by 2 to the 256. And for this, we have to compute rho of 256 divided by 16. And although this rho function doesn't have a closed form, yeah, computer algebra packages like Sage or Magma can compute this function for a given input, at least small inputs as we have here. And the probability here actually would be roughly 2 to the minus 70. So yeah, it's more or less hopeless to find to find a smooth integer with just picking random numbers. So the naive method of just picking one smooth number of the correct size and then hoping for one neighbor to be smooth is 2 to the minus 70 here for these parameters. So yeah, we won't ever find anything here. So this is basically a pie in the sky. Okay, so what else can we do? How can we improve these probabilities here? So the main idea here is that we search through pairs m and m+1 that split into smaller factors. Okay, so we're applying some more structure here. So we're using some structure that guarantees us that both m and m+1 split into smaller numbers. And then we can compute by the Dickmann-de Bruijn function that this actually gives us quite some benefit here. The main question is how can we pick such a structure that splits m and m+1 into smaller factors? And yeah, how would you split it into smaller factors, like larger factors or only small factors, many of them, or what would you do? There's a proposal here by some guy. Turns out that this approach of cutting the pie up is not the best. That was actually the first I thought of when Klein told me to include some pie jokes. So again, sorry for that. But I really love the cartoon movie, by the way. Watched that at least 1,000 times as a kid. Okay, so let's look at some examples of how we can achieve that. So we're gonna look at smoothness probabilities for 256-bit numbers again, and the smoothness bound being 2 to the 16. And one approach that Craig used in the B-side paper is the extended GCD method. So here we would pick some smooth and co-prime alpha and beta of roughly the same size. And then we would compute by the XGCD integers R and S such that alpha S plus beta T equals 1. We'll have that because alpha and beta are co-prime. So we will get 1 on the right side of this equation here. And then we can use the absolute values of alpha S and beta T as our twin smooths that we want to have, right? So basically, we pick those 2 green bars. They stand for those alpha and beta. And those orange ones are the ones we hope to be smooth, right? So we pick those alpha and beta of roughly 128-bit in this case, which are guaranteed to be smooth because we picked them as we wanted. And then we hope those other 2 factors of 128-bit each to be 2 to the 16 smooth. We can compute that again with this Diekmann-de Bruijn function. And turns out that here the smoothness probability for both of these orange bars is 2 to the minus 50 roughly. So that's already much better than the 2 to the minus 70 that we had before. But there's another method that Craig proposed in the B-side paper. We could also use polynomials x to the n, because here x to the n minus 1 often splits very favorably into small factors. So in this example, we have x to the 4 as one of our numbers, and x to the 4 minus 1, and this splits to x minus 1, x plus 1 times x squared plus 1. So essentially now we only need 3 64-bit numbers to be smooth and one 128 number. 128-bit number here to be smooth. And again, we can compute the smoothness probability here, and that would be 2 to the minus 48 roughly. Of course, we could also pick some smooth x value right away here. But basically, we want to have a probability for all of them to be smooth and compare that to the search interval that we have, right? Because here we want to input 64-bit numbers. So we want to compare that against the smoothness probability to see if actually we can hope to find something here. And the idea that we then had is, well, why not use fully split polynomials? So use polynomials a of x, which is a product of those factors x minus ai, and b of x product of those x minus bi, with integer roots ai and bi, such that their difference is 1. So this would give us even more advantage, because then if we had such polynomials for degree 6, this would split into smaller factors, or 12 of them this time. But anyway, even if there's so many factors here, the smoothness probability will be better than above. So it's 2 to the minus 41 for degree 6. And if we had polynomials of degree 8 here, then it would be even better. It would be 2 to the minus 27.3. And that's a pretty good chance for finding twin smooths here, actually. Because those 16 numbers that have to be smooth here then only are 32-bit numbers each. And then we have pretty good chances that all of these are 2 to the 16 smooth. Okay, but then the main question is, how can we find such polynomials that split into those factors and that differ by 1, that constant difference 1? And well, at first we tried to kind of solve that directly using something like Maple. But turns out that for degree 2, this is easy, but as soon as you move to degree 3 or 4, this gets very, very messy. But at some point, we found out about a nice number theoretic problem. It's called the Prouhet-Tarry-Escott problem. Pardon my French, but the first 2 names are French, and I'm not really good at pronouncing those. So in short, it's the PTE problem. And it says that given a size n and a degree k, we want to find distinct multisets of integers a with those ai's and capital B with those bi's, such that the sums of these a's and the sums of b's are equal, but also the sums of the squares should be equal, sums of the cubes should be equal, and so on, up to the sums of the k powers of all those elements. And if we have such a solution, then we write this in those brackets here with the degree here. Yeah, and by distinct multisets, we mean that an element can be in such a set A or B multiple times. But an element cannot be in both A and B, because then the problem would be, yeah, kind of trivial. Okay, so it looks, for at least for large K and large N, it looks pretty difficult to solve that problem. But here's an example for size 6 and degree 5. So there's 0, 5, 6, 16, 17, and 22 on the one side, and 1, 2, 10, 12, 20, 21 on the other side. And then actually those equations hold for up to the 5th powers here. So that's, yeah, a pretty neat example. You might already observe some structure here in these solutions, and actually most of those solutions have some special structure, but I'm not going to get into all the details here. Yeah, because we want to, yeah, find out about the connection to twin smooth integers and eventually to isogeny primes here. So solutions where k equals n minus 1 are called ideal solutions. And that's because you can easily prove that k cannot be larger than n minus 1 here. And those solutions are actually known for n up to 12, excluding n equals 11. And actually for all of these sizes except for 9, I think there's an infinite number of solutions that can be generated. Especially the cases 10 and 12 are pretty funny, because you can generate solutions by finding rational points on some elliptic curve. So that's kind of, yeah, funny coincidence, so to say, that we were looking for isogeny primes to do something with elliptic curves, then move to some old number theoretic problem, which then led back to elliptic curves. So elliptic curves seem to have a finger in every pie. Okay, so what we want to do with those ideal solutions then is we define polynomials a of x, which is exactly the product of those x minus ai, and the same for b of x with the factors x minus bi. And then there's a theorem that tells us if we have an ideal solution, then those polynomials actually differ by a constant c. So this is almost what we wanted to have. So we wanted to have difference 1, but here we get only some constant c, and this constant c will not be 1 for all n larger than 2, at least. For example, in this solution of size 6, we have these two polynomials, and the difference is 14,400 here. And for this size, it actually doesn't get better. You can compute lower bounds for those constants. But the good thing is that they are always smooth. Like in this case, where it's 2 to the 6 times 3 squared times 5 squared. And that will turn out to be pretty useful. Because since we cannot have difference 1 here, the obvious solution is to divide by this constant, right? So for these ideal solutions and these polynomials connected to them, we then simply define AC of x as a of x divided by the constant c, and BC of x as b of x divided by c, which means that their difference now is 1. And in case those are integer values, they will not always be integer values, of course, but since the constants are always smooth and the values of a of x and b of x we're going to look for are smooth as well, we'll have pretty good chances that these values are divisible by c. And if they are, then we get m plus 1 and m as AC of x and BC of x. And then we actually managed to to get those two neighbors, m and m plus 1, which split into n roughly equally sized factors. And we land in this nice case where the probabilities for finding twin smooth is pretty good. So what we then did is basically an algorithm in two phases, where the first phase is to identify B-smooth numbers in a given interval. And the second one is to check if some PTE solution aligns with the smooth numbers, right? So we have m and m plus 1 that's split into smaller factors, and we want all of them to be smooth. And the first step we did was to identify those B-smooth numbers in a given interval. What we did here is to use a sieve. It's standard technique, pretty much reversing the prime number sieve. I think we can go over this quite quickly. So if you want to identify the 7 smooth numbers in this interval here, we start with writing an array where every entry will be 1. And then we start with multiples of 2. And we only have to identify the first number in the interval that is divisible by 2, and divide this index by multiply this index by 2. And then every second element of our interval will also be multiplied by 2. And we do the same for 2 squared. So every fourth element will now be multiplied by 2 again. Then every eighth will be multiplied by 2 again, and so on, until, in this case, we reached 128. Even 256 is in there, but 512 not anymore. So we can move on to multiples of 3. So again, we identified the first number that is divisible by 3. Its index will be multiplied by 3, and then every third element will be multiplied by 3. And we update that again with the powers of 3, 27, 81, that's even 243, and 729, and that's even 3 to the 7. And then we do the same with multiples of 5, and multiply all those here until we don't find any suitable number in our interval anymore. And then we do the same with the multiples of 7. 7 squared, 7 cubed, there's nothing more to do here. So now we're done, because we wanted to look for 7 smooth numbers. And now if the index equals the number that we presented, then this means that this number is 7 smooth. So in this case, it's only those two, 4,374 and 4,375. And yeah, we were super lucky because those are actually smooth neighbors. And then we can simply write this as a bit string with a 0 if a number is not smooth, or 1 if the number is smooth. And that will be very useful for the next phase, where we want to align PTE solutions with that. So again, the same example with a PTE solution of size 6. There, our polynomials will have all these factors, so x minus 16, x minus 15, and so on, up to x. So it's always x minus those entries here. And this one is pretty useful because it has repeated entries here. So it's actually only 9 factors in total instead of 12. But there's some theory that tells us that we can't do better than having squares here. So we can't have a number in here more than twice. And then this corresponds to the specific bit pattern here that we want to find in our interval, right? So the distance between this, these are neighbors. The next one for x minus 2, we don't care, but x minus 3 is important again. We want all those factors to be smooth. So we have to find this pattern here where all those x's, we don't care about if those numbers are smooth or not. And so for this example that we just saw, but this time an interval of larger numbers here, on top, you see all the numbers in our interval, and below them, you see if they are smooth or not. And then we want to find this bit pattern here. So we align that with some 1 here in our bit string of smooth numbers, and check if all the other numbers are smooth as well. In the first case, they are not, so we're moving on our bit pattern here, align it to the next one, but then we see that the neighbor again is not smooth. Then we align it to the next one here, and so on, until here we are very lucky to find one that matches, and actually all those factors here are smooth. So this gives us a good candidate for producing 2 to the 15 smooth neighbors here. But still, we have to check for divisibility here. But turns out that those are divisible by C. So we actually found twin smooth neighbors m plus 1 and m. And also their prime, their sum here, which will be defined as P, is prime. We are very lucky again here, surprisingly. So this would be a good candidate for using it for P-set, for example. And this here is the factorization of P plus 1 and P minus 1. So yeah, you can see that their factorizations are, yeah, only consist of small factors up to 2 to the 15, which would be 32,000 something. All right, so to wrap up this part quickly, we implemented that in Python. The sieving technique here, where the sieving step is done in C. So it's pretty fast. Thanks also to Patrick Longa for helping with that. And we can actually check many PTE solutions in a single sieving step. There's some more theory behind this. Arranging PTE solutions in trees and things like that. So pretty fun, actually. What we did find, the best things we found was 256-bit primes with 2 to the 15 smooth neighbors, so like the one we just saw. And for larger security levels, like 384-bit primes with 2 to the 21 smooth neighbors, or 512-bit primes with 2 to the 29 smooth neighbors, which is pretty good. And yeah, results are much better than the other techniques I showed you before. And also it allows for a variant with non-smooth cofactors, and that could be useful, especially for the case of SQISign, as we will see later. All right, so let's get to the next part here, which will be constructing twin smooths. So this time we're using a different technique for finding those twin smooth integers. So there's one technique first by Stürmer. So consider we're having twin B smooth integers r and r plus 1, and we define x to be 2r plus 1. So their sum simply. And then let d be the square free part of x minus 1 times x plus 1. X minus 1 times x plus 1 is exactly the number we want to be smooth. So it's the product of the neighbors of this x, which would then be the prime that we use in isogeny crypto. So we can write x squared minus 1, which is this product, equals d times y squared. And then Stürmer reverses this argument and says that we can simply solve Pell equations of the form x squared minus d y squared equals 1 for all the 2 to the pi of b possible choices of d. Okay, so d is square free. We want it to be b smooth. So there's exactly 2 to the pi of b choices we can make for this d. And since we can write all b smooth integers in an equation like this, we actually find all of the twin smooths in this way. So if y is smooth here, then we will have a twin smooth here, because then actually also this x squared minus 1 is smooth, and so is x minus 1 times x plus 1. So as I just said, this method finds all of the B-smooth twins here. So that's very useful, but requires solving 2 to the pi of B Pell equations. And yeah, that's sorry. Yeah, Craig solved this up to B to the 113 in his B-side paper, but that's not nearly large enough for cryptographically sized parameters, and yeah, it's basically hopeless to compute this much for much larger smoothness bounds, because the compute time just explodes with this 2 to the pi of B. So we have to find some other methods for finding twin smooths of appropriate sizes. And there's a nice paper we found by Conrey-Holmstrom and McLaughlin that introduces what we call the CHM algorithm. And they make a pretty simple observation here. So given twin smooth R and R plus 1 and S plus 1, where R is smaller than S, we often, for some definition of often, find that if we multiply R divided by R plus 1 with S plus 1 divided by S, then we can sometimes bring that to the form T over T plus 1. And if this works, then yeah, actually we found new twin smooths T and T plus 1. And this simple observation gives us an idea for a nice algorithm, the CHM algorithm for finding B-smooth numbers. So we start with some initial set S0 that contains all the numbers from 1 to B minus 1. And each of these numbers in the set represents a pair of twin smooth integers. So 1 actually represents 1 and 2, because they're obviously B-smooth. And B minus 1 represents B minus 1 and B, which also are B-smooth. And what we now can do is simply check this equation up here for all the pairs R and S, which are both in S0. And then all the new solutions that we found with this equation above, we include those in the set S0 and call that set S1. Then simply repeat this again and again until some iteration doesn't produce any new twin smooths anymore. Okay, that sounds pretty simple, and it's not clear at all that this will produce anything useful. So let's look at a small example. 5 smooth twins. Here we would start with the set S0 containing the numbers 1 up to 4. And then there's 3 pairs that produce new twin smooths. We have this CHM equation. It's the pair 2, 3, 2, 4, and 3, 4, which produce the new twin smooth pairs 8, 9, 5, 6, and 15, 16. So we add those to the set S0 and call it S1. Then we just repeat the step and check all combinations again. And here actually find the pair 9, 10 and the pair 24, 25. And then we repeat that again. And we find one more, namely the pair 80, 81. But then for the next step, we don't find anything anymore. So yeah, maybe we just got lucky and found a couple of twin smooths, and there are many more of those 5 smooth twins. But actually here, this is the full set of 5 smooth twins, as I also showed you in the introduction. But still, this is a very small example, and it's not really clear if this really scales to larger smoothness bounds, or if we're just very lucky in this very small example. So main question is, does this scale to larger smoothness bounds? And what they did in their in their paper, in this paper by Conrey-Holmstrom-McLaughlin, is they ran it for B equals 100 and found more than 13,000 twin smooths, which is already a bit more impressive than the handful of twin smooths we found for smoothness bound 5. But also we can run the Sturmer approach for this size, and it turns out that we already we only miss 37 of the twin smooths that exist for b equals 100. So that's a pretty good ratio. But it gets better because 36 of these are found if you run CHM with b equals 200. So sometimes those later steps, those larger factors just cancel out, and we will get 100 smooth neighbors. Sorry. And they even prove in their paper that we would find the last one for b equals 227. So they ran it also for b equals 200 and found almost 350,000 twin smooths. So sounds pretty impressive. So this produces lots and lots of twin smooths. Maybe not all, but then the conjecture is that this algorithm finds almost all twin b smooth integers, or again, some definition of almost all. But still the question, and I really like this because they do quite a bit of analysis and give some really other problems, and then the conclusion says the unanswered question in all of this is, why does it work? And basically, we don't have an idea. But we implemented this algorithm in C++. I mean, Giacomo did a really good job with that. And we ran it up to b equals 547. And this plot here shows the number of twin smooths that this algorithm finds by the smoothest bunch, where the scale here is in 10 millions. So at 547 smooth twins, we have more than 80 million twins. So the number of twins really explodes here. And yeah, this already gives an intuition that at some point, both running time and memory will be a problem for increasing the smoothest bound even more. But more interesting, how large are the twins that we found and what's their size distribution. So on the right side, we have the distribution of the 199 twin smooth pairs. On the left side, we have the 547 smooth pairs. And in both cases, this roughly resembles some kind of normal distribution. And what we observe is that this peak that we see here grows with every iteration of B and slowly walks to the right. So if we look at this right plot, this will be included somewhere here, somewhere short of 40 bits. There's some really small peak here, which are the 199 twin smooth pairs. So for iterating this B even more, this just becomes a larger peak that even goes further to the right. Okay, but what about the largest twin smooth pairs? Because that's what we're mainly interested in, right? So our aim was to construct really large twin smooth pairs of 256-bit or even more. But actually the size grows like painfully slowly. So for 547 smoothest bound, we only found a twin smooth pair of roughly 121 bits or something like that. So we are still very, very far from reaching our goal. And some extrapolation of the data suggests that we need to go somewhere in the low thousands at least to hope to be able to hope for 256-bit twin smooth or something like that. So actually, it's hopeless to run this algorithm that far, because then runtime and memory requirements will just explode. But what we did is we found some optimizations and applied those to our code. And the idea was to sacrifice the completeness, because we don't need all twin smooths for finding larger twin smooths. And there's some observations that we made. So we only get new twins that grow in size if those R and S that we plug in satisfy that S lies between R and 2R. But also we have better chances if R and S are k-balanced for some small k, or k close to 1, where S lies between R and k times R. And with that, we define some variants that only check, for example, only check those pairs that that are k-balanced for some choices of k close to 1. But those waste lots of time for those size checks to check if S actually is smaller than k times R. So we implemented one more variant, the constant range variant, where we keep the set sorted all the time and always check a fixed number of neighbors of each R, which of course are the numbers that are the closest to R in size. And we even defined some other variants and tried a lot of things here. Problem is that we don't really have a theoretic handle on what's happening here. But those two mentioned above seem to be the best in performance. And here's a small table for those two variants. So for the full CHM algorithm for smoothness bound 300, we had a runtime of 4,700 seconds and found 2.3 million twins. And with aggressive choices of this global K method, like K equals 1.05, we have a speed up of more than 170, but still find 2.2 million of those twins. And of the largest 100 that the full CHM algorithm finds, we still find 65 of those. But the numbers are even better for the constant ranges approach. There we reach a speed up to 294. Still lose only roughly 10% of the twins here, but find even more, a larger ratio of those largest 100 twins than the global K method. Okay, so as a wrap up, even with those optimizations and larger smoothness bounds, we are still not able to generate twin smooth that are larger than 2 to the 200. But we are able to generate lots of twin smooths below 100 bit, and even with our optimizations, some twin smooths up to 128 bit. So the main question arising here is this still somehow useful to generate these SQISign primes? And with that, we come to the final part of this talk. And now we can actually talk about SQISign, at least the SQISign prime requirements. So for the SQISign prime, we want 256-bit prime for NIST-1, 384 for NIST-III, and 512 for NIST-V. And as we've seen in the motivation before, we want to have enough accessible torsion for everything to be efficiently computable. So what we want is a B-smooth factor T prime, which splits to 2 to the F times T, which should divide P square minus 1. So this means that the full T prime torsion, so the full 2 to the F torsion and full T torsion, is defined over FP square on the curves or its twists, and we can use all of them and can efficiently compute isogenies of those degrees on the curves of their twists. And the SQISign requirements say that T should be at least P to the 5/4. For some more details on that, I can recommend Antonin's talk from the first season of the Isogeny Club, where he talked about where this requirement comes from. And also we want F to be as large as possible. That's again some efficiency related thing. For example, for the verification of SQISign signatures, it's very important that this for efficiency, it's very important that this F is as large as possible. And there's some signing cost metric that is introduced in the SQISign-2 paper that says that the cost metric for the cost for signing is roughly equivalent to square root of B divided by F. So this is only a very rough metric, but we can at least use it to compare different primes that we find here. Okay, so what are we doing for using the smaller twin smooths is we use primes of the form 2 to the 2 times xn minus 1. So again, we use those x to the n polynomials. And this time we plug in twin smooths x minus 1 and x. So for n equals 2, we want p squared minus 1 to be smooth. And this factors in this case is 4 times x squared times x minus 1 times x plus 1. And if we plug in a pair that is smooth already, then we have x and x minus 1 being smooth. So by construction, we already have a smooth factor t prime of size p to the 3 over 2. So this already gives us enough smoothness for satisfying these requirements by SQISign. But the twin smooth we have to plug in only have to be half the bit size of the prime that we actually want in the end. We can do the same with n equals 3, and this factors like this. So we get a smooth factor t prime of size p to the 4 over 3 guaranteed. And we can continue with n equals 4, with this gives us a smooth factor of size p to the 5 over 4. And we can go even larger, but then the guaranteed smoothness decreases. But again, we can hope that some of these other factors will have some smooth prime factors, so that actually we find some larger smooth factor than p to the 7 over 6. So in a nutshell, we can just plug in smaller twin smooths that we found by CHM or PTE to generate SQISign-friendly primes. And now I just want to show you some examples of the best primes that we found in this case. So for NIST-I, we used x to the 4 polynomial and plugged in a twin smooth number found with CHM, so with the full CHM run, and here in this case it's 467 smooth. And then we get those factorizations for p plus 1 and p minus 1. So we see that this is 479 smooth. Smoothness bound is different from this one because this comes from some other factor that is involved here. And the gray ones, we don't actually have to use them in SQISign. So with the black numbers here, this factor t is already, log p of this factor t is already 1.3, where we needed 1.25, so this is already large enough. And the signing cost metric is 0.45 in this case. For comparison, the prime that is currently used in SQISign has a smoothness bound that is somewhere around 3,900 and has this signing cost metric of roughly 0.9. So the one that we found looks better, but actually we don't know if it will perform better in practice because it's, the current SQISign code is not really made for plugging in different primes. So it's and that prime has a larger power of 2 and also some nice large power of 3, which is also useful. So as I said, the signing cost metric is pretty rough. So maybe this will be faster than their prime that they have right now because we have a much smaller smoothness bound. But we can't really be sure. But then again, for NIST-III and NIST-V, our method is actually the first that generated some practical parameters. So in this case, we used x to the 6 as the polynomial, and a 547 smooth pair of twins that has 64-bit in this case. This factor t will have smoothness bound 10,243, where again this comes from some other factors here. In this in p squared minus 1. And here the signing cost metric is 1.28, and the smooth factor t is again of a good size to be applicable to SQISign. And then there's one more example for NIST-V. There we have a 508-bit prime found with the x to the 4 polynomial. This means that we had to use roughly 128-bit twin smooths, and we didn't find really many of those with CHM. So we used the PTE approach. so the approach of the first part of this talk, and some twins with smoothness bound 15,263 in this case. And yeah, we'll find this nice prime where the smooth factor T actually has the smoothness bound 15,000 here. So this is a pretty good result, although the power of 2 here is relatively small. So we also found some other examples with larger smoothness bounds, but larger powers of 2. So yeah, it's really up to, yeah. At some point we'll have to try and plug them into SQISign. But yeah, as I said, the current code is not made for plugging in different primes, and especially not made for plugging in larger primes than NIST-I primes. All right, so quick wrap up. So with the CHM method, we can find lots of smaller twin smooths. And as I showed, we can construct SQISign primes from smaller twin smooths as well. But the performance gain still unclear, as I said. Looks pretty good. The signing metric is pretty good for NIST-I. But yeah, we're not actually sure if this improved things. And then we gave the first practical parameters for NIST-III and NIST-V. And now I went a bit over time, but that's it now. So thanks for your attention, and I'm happy to answer questions.
Thanks for the talk, Michael. As always, if anyone has any questions, you can unmute or type in the chat or whatever. Anything you feel like. Yeah. If I can start with the question, it's like way back in the start, you talked about these PTE solutions and that they only exist for like up to 12 except for 11. Is that like proven, or is it
I know. So these are the ones that we know. There's an old conjecture that those ideal solutions should exist for all n. But then there's some more analysis and some other work, and there the authors say that they don't believe that this is true, and actually it seems we were more than lucky to even have those solutions of those sizes. So it's not really clear if there's also ideal solutions for our sizes.
Cool. Just weird that it kind of like skips 11 also.
Yeah, true.
Oh well, let's give some. Yeah, Francisco has a question. Do you want to read it yourself, or I can read it out loud so that also the people on YouTube can hear it. So Francisco asked, well, first of all, he says, thanks for this super nice talk. And then the question is, what was the computational time associated with finding the SQISign primes?
So for finding these SQISign primes, after you already found the twin smooths, that's negligible basically. So there you only have to plug in the twin smooths of suitable size into those polynomials, and then do some trial division or something like that. But that's actually not too many twin smooths you have as candidates there. So that's more or less negligible. So the main task is to find those twin smooths here, and yeah, looking at these graphs here. I think for the full run with this 547, this ran for a couple of days, I think, on something like 64 core server or something like that. I don't remember exactly. I think we have some details in the paper. For the optimized variants, we ran this with smoothness bounds up to, I think, 2 to the 11, so 2048. But using some very aggressive choice of this constant range approach. And ran this for something like 2 days on a big server or something until it completed, and it found something up to, I think, 150-bit twin smooths or something like that. But the problem is it doesn't really find many of those larger ones. So that's why here in this example for NIST-V, we also resorted to generating twins with PTE, although the smoothest bounds are larger here. But of course, with more computing resources, yeah, we could actually run CHM a bit further. But also the memory becomes a very big problem at some point.
Yeah, thanks for the nice answer. So Craig also has a question and asks if we make the assumption that the best method of finding these pure twins is still out there, and if you had to bet one way or the other, would you bet that constructing or searching/sieving will end up winning?
That's a very good question. I think that depends on the goal. So the goal is to find SQISign primes or twin smooths.
In the question, it's finding pure twins, like
finding pure twins.
Yeah.
Yeah, I don't know. It always depends on the smoothness bound, right? So if the smoothness bound is somewhere close to what we achieved with CHM, then maybe you can optimize a bit more and push this a bit further. But if it's far beyond that, then it's definitely the search methods with PTE or something like that. Well, I think
And
this depends
if
a bit on the smoothness bound.
Sorry, what was the last part?
I think it really depends on the smoothness bound.
Yeah.
That you want to achieve.
Yeah, I agree. And if you have an answer for SQISign primes, that would be interesting to Craig adds.
For SQISign primes, well, currently it looks like this CHM approach is the constructing approach is very useful, combined with this method of boosting primes here. So I would say for SQISign, this is currently the best method that we have. But of course, there could be much better techniques. So it's still an open field for research, definitely.
It's very fun that this problem is so easy to state, but seemingly very hard to solve.
Yeah, definitely.
Yeah, if there are no further questions, then I can thank Michael again. And I'll stop the recording now, but if anyone wants to just hang out and have a chat with us, then we'll keep up the Zoom meeting for at least a few more minutes. Unless you
and let me add to that before we end the recording. Yeah. That actually next in 2 weeks we have a talk by Prouhet-Tarry-Escott with a very cool title called SQISign HD, signing with higher dimensional isogenies, about using the Castrijk-Leroux, Minor Martindale, and Robert attack constructively to sign in SQISign in higher dimensions. And with that, I think we can wrap up for today. But yeah, do hang around if you wanna chat a bit more, or also wonder about the Eurocrypt, what we're planning there, or anything else.